Welcome back to another lecture in the RSLogix 5000 Studio 5000 series. This particular lecture is where the fun starts for many people. Personally, as I said earlier, the one-shot is my favorite instruction, but I do remember, many years ago when I first started, it was a big deal when I got to timers and counters, because that adds kind of a suspended animation in your logic. Well, timers and counters there's a reason that they look so much alike. When you look at the data types and the structure, the only real difference is the trigger, or rather what the instruction does when the rung is true. They both count. Timers and counters, those instructions count. One of them counts events and the other counts units of time. Now, in the older PLC platforms, you could have had 1,000th, 100th, 1/10th, or 1 second time base, meaning that you counted 1 second transitions, 1/10 of a second, 100th of a second, or thousandths of a second pulses or transitions. But in reality, if you use 1,000ths, well, you can always use 1 for 1,000ths, 10 for hundredths, 100 for tenths, and then 1,000 thousandths of a second for 1 second. So the only real difference between the timer data type for the 5000 platform and the older is that you only have one time base. That's 1,000ths of a second. So let's get into timers. Timers, counting units of time, counting increments of time. Well, yes, you even count units of time when you are timing something. You count seconds, sometimes minutes, and on occasion you count hours. You might count units of time for an interval and accumulate days, hours, minutes, and seconds as the result. The Logix engine counts 1,000ths of a second. No minutes, no hours, and definitely no days. You are required to do the math if you want days, hours, minutes, and seconds. Or, much later on, we will demonstrate the GSV instruction to get system time. So the GSV is get system variable, and you can use a GSV instruction to get system time, including the date and year. The first instruction that we're going to deal with is a TON, on delay timer or delay timer on, whichever way you like to say it. Now remember, there is only one timer data type, and we have 3 instructions that we can instruct an instance of the timer data type with. The original intent of this instruction was to delay the on state of a bit in memory for the length of the timer's preset, delay on, after initiating conditions were true or after an event occurred. Originally, these were relay timers, and when you energized the initiate or start input or screw terminal on this timer relay, it started a timer, and you would set the timer in the older ones with a little knob on front, and it was not very accurate. The accuracy depended on the span or the maximum delay. So if you had a maximum delay of 1 second, then you could probably set it fairly accurately to tenths of a second. If the total possible delay was 10 seconds, then you could probably set it fairly accurately to single second units. This is what we have now, our 3 timer instructions, and they can all be found up here, TON, TOF, and RTO. There's your counter instructions and the reset instruction that will reset any of these. I had you create a new project named beginner L, whatever your processor number is, TON. Now you can see up here I named mine Pt1_00 so I could have different versions of the same lab when I save them. Be sure to point it at the folder that you created in which to store your learning projects. So when you save your project, make sure you save it where you are expecting it to go, not just do save as and hope it goes where you want. Add the digital I/O modules needed to give you a few inputs and outputs. And as always, we are using the 1769 IQ6XOW4 for our instance of module-defined tags. Open both the controller tags and the program tags databases to ensure that they are both empty, with the exception of the module data type instance for your I/O modules. Now I already created my time here, so I'm just going through the instructions. So if we open up the controller tags, see there's nothing there but the I/O. And if I open up the program tags, you see there's just my time. This tag right here. It's repeated in the watch window. And I did ask you to open up the watch window and arrange your display for easy viewing of the rung and the watch panel. Now, the next step was to download and go online in the run mode with your single rung of logic. If the processor is in the run mode, the TON instruction will execute, accumulating 10,000 times 1,000ths of a second in 10 seconds. It accumulates up to 10,000 at units of 1,000th of a second, and at 10 seconds it will time out and be done. Now until the accumulate equals the preset, it will stop. Once the preset is met, the accumulates up to the preset, then the timer stops. At this point your display will show 10,000 in the accumulate and the done bit. Right now you're not seeing any of that because we're still offline, because I wanted to demonstrate something. Notice that this is 0 and that this rung is unconditional, which means the rung is true. This is not a counter. Now this is a timer that counts units of time. I'm going to go communications, who active, download. Notice how fast this is going compared to earlier downloads. That's because we have an Ethernet controller and we're communicating at 100 meg instead of 38.4K. What we missed while I was talking was this accumulating, and because it came up with the error page, it pushed out the logic up here. So I'm going to do that again. To do that again, first I'm going to put it in the program mode. So I did it with a key switch up here. We're in the remote program mode. I'm going to click there, 0, enter. Now when I go to the run mode, and by the way, that doesn't really reset the timer. See the done bit and everything, that's still on. So I'm going to go here, set that to 0, set that to 0. That's the way it looked. Now I'm going to put it in the run mode. I'm going to change it from the remote program to remote run. Watch the enable bit and the accumulate, the timer timing bit, and the done bit. It's accumulating. The enable bit is on, the timer timing bit is on, and when it gets to 10 seconds, the timer timing bit is off. It's still enabled, but the done bit is on. Now it's still enabled because this is a unconditional rung. The rung is still enabled. So I said keep a close eye on the watch panel during this next step using the key switch on the controller or from the online toolbar. Toggle the processor to the program mode, immediately go back to the run mode and watch the accumulate value in the rung or in the watch panel. So I'm going to do that again. Notice it reset it because the initial condition, the pre-scan, is to set it to false, the rung. We have 10 seconds in there to give you time to peruse these bits and values down here. One more time, we're going to do this, the first thing you're going to see is enable and timer timing. See, timer timing and enable. You see it accumulating, and when it gets to 10 seconds, it is no longer timing. It's still enabled, but the done bit comes on. So do this several times and make sure that you follow all this. With one eye on the watch panel, with the instance of the timer data type expanded, select the accum field on the timer instruction and type in 0. You click there, 0, enter. Did it remain at 0? Yes, it did. Did the timer start accumulating again? No. Why? Well, we really haven't discussed it, but the done bit is your clue. When it's done, it's done. Clearing the accum does or does not reset the timer function. It does not reset the timer function. If you change the accumulate value to a value lower than the preset, after it's done, it's not going to reset it. I'm going to do something that I did not do in the manual. I'm going to select the accum down here. I'm going to reset this with my key switch. I'm going to reset it again with the key switch. I'm going to put in 15 seconds to give me more time here. Okay, so I'm going to reset it. Remember, it's still done. I'm going to reset it though, so it starts over. I'm going to go here and put in a value of 1000. Now, I can consistently drop the accumulate value and the timer keeps timing. See, I'm typing in a value lower than the accumulate. It drops it back down to that and then starts counting up. Whatever value I type in, as long as it's not done yet. Once it hits done, and of course I put in 150 seconds instead of 15,000, so it's going to take a while to get there. So just for grins, I'm going to change the preset back to 10,000. It's instantly done. If I can do this from the keyboard, I can do this from the logic as well. In other words, I can write a value to the accumulate or to the preset anytime I want, even if this timer is timing. Now that's more of an advanced subject. We're not going to go any further in that direction right now. Clearing the accumulate does or does not reset the timer function. It does not. With one eye on the watch panel, set the accum field on the timer instruction and type in 10,000 in the accum field. So what we did was we made this 0 to show that it doesn't start timing again, right? And then we put in 10,000. With one eye on the watch panel, select the done bit value in the watch panel and type in 0. Now this is a little different. So we're going to put in a 0. Did the done bit accept the state change? Yes. Did you see any changes? Yes. The timer started timing again, because remember that this little chunk of code that you can't see, but it's buried inside of this instruction, if the done bit is not set on the very next program scan, it starts incrementing, and then it compares the preset against the cumulate, or the cumulate against the preset. Well, it had time to accumulate one more thousandths of a second. And of course, instantly compare the accumulate against the preset and set the done bit and stopped accumulating. It is possible to get some sort of funky behavior out of these timer instructions instructing a timer data type if you start tweaking the values with logic. Now I did it from the keyboard, but I could just as easily have moved values in. I could have a button that clears the done bit. In other words, I could add a rung right below here. And we'll go back to bit, put in something like that, something like this. Then I'm going to drag my time down to here. .dn. That's an unlatched bit. You recognize that. And we'll just call this junk. It's a junk bit. Finalize all edits. Okay, the done bit is on, right? So when I toggle this, look what it's doing. Every program scan, it's unlatching the bit, so it just keeps right on counting. We just show you this kind of junk, literally, to illustrate that instruction and its limits. Okay, it's gone. And we'll put this back at 10,000. The last, whoops, 1,000. And the last thing we did was go to the watch panel, set the done bit to 0, and it counted up 1 more thousandths of a second. Did the timer instruction resume incrementing units of time? Yes, it did. The answer to that last question may vary, but normally if you clear the done bit directly from the keyboard or with logic, it will resume for possibly 1 scan and realize that it is done and set the done bit again. But you will not see the transition. The only reason you might realize that this happened is that the accum is now greater than the preset. This type of manipulation of the members of a timer data type is not supported. It's not recommended. If you do something like that and have problems, you call up Rockwell Automation and they'll just say, well, we don't support that. Clear the accumulate first and then set the done bit to 0. Okay, so we can clear it here or we can clear it here. We'll clear it down here. And now set the done bit to 0. And you see what it does. Did the timer instruction resume counting units of time? Yes. Why? 2 reasons. The first one is it wasn't done. The second one is that the accumulate value was lower than the preset value. Now in the previous little exercise it did the same thing, but because the accum already equaled the preset and it started incrementing by 1, it was immediately done and you never actually saw it accumulating. And another reminder, there is only one data object that backs timer instructions. It's called the timer data type. There is a TON, TOF, and an RTO instruction. There are not 3 unique timer data types, but only one data type that can be used as an instance to back 3 unique timer instructions. Or rather, you can say that there's only one timer data type and it will respond to any one of those 3 or any combination thereof of those data types. So you could use a TON, a TOF, and an RTO and use the same timer data type. Now you're going to get trash is what you're going to get. That's not recommended or supported. For each timer instruction you want a unique timer data type, an instance of a timer data type. While watching the state of my timer timing bit, the TT bit, in the watch panel, cycle the processor to the program mode and go back again. See, the timer timing bit is on. How long did the timer timing bit stay on? Well, it's still on, still on, still on. Okay, it's off. Well, it's easy to answer. Whatever the preset is, the accumulate starts at 0 and the timer's timing until accum equals preset. So 10 seconds or 10,000 1,000ths of a second. Repeat the last step again while watching the timer timing bit before you cycle the mode. During the accumulate and after the done bit changes back to on. So watch it now, now, and then again after the done bit is set. How long do the timer timing bits stay on? 10,000, 1,000ths of a second. Was the timer timing bit on before you cycled the mode? No. Was it on after the timer data type had accumulated to a value equal to the preset? No. Now these may seem like simple questions, but rather than just lecture and tell you here's what it does, I would rather demonstrate it, have you operate it, and then you answer questions. That somewhat guarantees that you followed, noticed, made note of the behavior. So then we had you save this project. Because we're not changing the name right now, it's just TON. We're going to hit the floppy disk symbol up there to save it. It was saved. And now we're going to do a save as. And we're going to change it to plus. We're on page roughly 189, 190, 191, somewhere in that area. And we said to save your project as beginner L, your processor number, TON plus. And then I said, just for grins, add 3 new rungs shown in the next illustration. Rather than pause and add those, I'm going to add one to show you the easiest way. True if on, energize output. We can drag down my time to this tag Mimi. That's not an instruction Mimi, that's a tag Mimi. And double click on it, click after it, and we wanted that to be the enable bit. So I'm going to hit decimal point. Now it comes up with preset. I'm going to hit E, and instantly you notice that with type forward it goes, oh, maybe they want EN. Hit enter, and you have it. And then of course this one is not a one that you can drag and drop. However, we're going to say that you're using OUT00, that you have those tags. Now we don't. So as soon as I click on it, it's undefined, new, and I'm going to make that alias to match what's in the manual, and I'm going to drop down to my outputs, data, and I believe it's bit 0. Create, and there you have it. Now we can finalize all edits, but we need to add 2 more rungs. So at this point, being one to do things as fast as I can, I'm not saying that you should do this. I'm going to click here, I'm going to go Control C, Control V, Control V to make 2 more rungs. I'm going to drag this down because we don't need that much watch window right now. Now what's going to happen is when we finalize all this, this is all going to go back to the errors window anyway. So we want this to be timer timing bit, so we double click, put the cursor at the end, backspace, backspace, T. As soon as we hit the T, you see the other T. Type forward, hit enter. And this, of course, is the done bit. So we can do the same thing here. Double click, click, backspace twice, hit D, there's the done bit, hit enter. Over here though, we can do something similar, out 1, of course there is no out 1 tag, and click here, out 2. So now we have output 0, 1, and 2, but we have to alias them. Now you're online right now. If you mess this up, you have to go offline to straighten it out. So we're going to go alias, and I'm going to go local, pops up, this is an output, data 1, and that one's good. Right click, new, alias, L for local, drop down, data 2, create. Now you see we have 3 happy rungs. Of course we haven't finalized the edits yet, but they're ready to insert. We hit the finalize all edits button, yes. And remember, this is not RS-232. This is Ethernet. So you see how much faster Ethernet is. Now if we go to watch, we have more tags to watch. So if we drag it up until they're all visible, I think that'll do it right there. Now we don't see much of our code. So we could ungeyser it until we can see all 4 rungs. That's one possibility. Another is that we could increase the height of this area by moving some of these menus, or I'm sorry, these toolbars, move some of them around. You see how it just jumped up? And we could put these over here. And we could also move this one. We can drag this one down to here. Now we have more height. Now we're big again, and these 3 are over here. Now personally I wouldn't do that, but because first of all I want you to know that you can do this. But most important, if you're using a mobile app, I want you to be able to see more. However, this text down here, you cannot increase its size. The only way I could increase this size is I would have to go change the parameters on my HD display to something lower resolution so everything shows up bigger. But then it doesn't look as clear and clean on the screen either. So this is the best we can do right here for you. Although that it is unlikely that you will actually use the enabled bit in a real application, you will use timer timing bit and the done bit a lot. The purpose of this lab exercise is to demonstrate the behavior of all 3 control bits of the timer data type. All timer data types, regardless of whether you are executing a TON, TOF, or RTO instruction against that timer data type, they all have these 3 control bits: enable, timer timing, and done bit. It may help to clarify this data type if you open the data types folder, the predefined that is, and double click on the class of objects called timer. So if I go over here to data types, I have to move this down, predefined, and then scroll down to timer, begins with a T right there, double click, see, name, timer, members, 12 bytes, you have a dent double integer for the preset, double integer for the cumulate, and then booleans for the enable, timer, timer, and done bit. You can't change this. This is a predefined data type. It's a class of objects that you can instantiate, which you did right here with my time. In the online run mode, with your new logic, make a note of the state of the bits that are now controlling outputs on your output module. Once duly noted, toggle the controller mode again and watch the bits. We've got enabled and done because this is already timed out, right? So I'm going to toggle the modes. I'm going to go program. You can see it right here. See, the key switch is over in the program mode. Back to remotes in the remote program, run, and back to the middle to remote run. And if you're watching the lights on your digital field device simulator, the top red one is lit and the middle green one is lit, and the middle one just went out and output 2 just went green. So now we have output 0 on and output 2 on. And you can see that down here. Output 0 is on, output 2 is on. At this point, you can stop and play with this instruction if you want, watching these 3 outputs, and we could actually operate it by adding a switch, which is what we're going to do. And you may reduce the preset if you find yourself waiting impatiently for 10 seconds to expire. So let's do that. Oh, first of all though, what order did the bits, the outputs, come on in? Watch and think carefully. Well, obviously the enable bit and the timer timing bit, it's almost impossible to know which came on first. But I would probably want to say if you're going to pick, I would make the enable go on, then the timer timing, then the done bit. As you read across, it'd be 312. You could debate that the enable and the timey bit come on simultaneously, and there's no way for you to really observe that. Let's reduce the preset to 3 seconds, 3,000 thousandths of a second. Notice that this looks like something's wrong there, but remember that this was already done. Now I had you save your project again. I didn't have you change the name, but I'm going to save it, and then I'm going to make a change and save it again. So I had you put in a switch here. Put that in the edit mode. Now you got to go down here and find your instruction set, and I call that input 0, so that'd be IN00. And of course we don't have that tag. You might if you're using replacement substitute tags. So we alias it. We go down to local 1 I data bit 0. Finalize all edits. Okay, now the timer's reset. And if I push, now on the digital field device simulator that I have, which is one that it's the same one that you can purchase on the website, my top input, which is a toggle switch, up for the toggle is on, normally closed, down is off, normally open. So right now it's down. If I push that red button right next to it, watch the timer. It's accumulating. I let go. So that's the advantage of having enhanced inputs on your digital field device simulator. As opposed to cycling the mode of the controller to enable disable the Pt1 instruction, toggle input 0 off and then on. To do that, I would use the toggle switch and just toggle it to the up position. Was there any discernible difference in the behavior of the TON instruction between cycling the controller's mode and just toggling the true-false condition of the rung with a switch that you have connected to input 0? I didn't notice any difference. I can't think of any difference. Disable the TO instruction. Look over the chart below and then enable the TO instruction. Observe and fill in the order of the events below, putting a 1 in front of the first in the sequence, a 2 in the second, and so on, that happens in whatever order it puts it. I would use a pencil lightly so you can erase your mistakes. Now remember that if two things happen simultaneously, or at least you think they do, well, feel free to do that. If you have a 1 and then 2 2s, because you think both those happened at the same time and they were second in the sequence, by all means do that. This is your learning experience. This is not a test. So let's do that. Okay, take a moment and fill in that chart. You may want to pause the video and then come back. Welcome back. Looking at that chart down there, think about how you operated this code. The first thing you do is turn on input 0. So input 0 is set to 1. It's at the bottom of the second column. That would be first. If input 0 is set to 1, then the rung goes true, which is the third item on the first column. Once the rung goes true, then the enable bit is set to on. The timer instruction has enabled the timer data type to execute as a T1 instruction. Once the enable bit goes on, then the timer timing bit is set and it starts to accumulate. So you could have accumulate increments and timer timing bit set to 1 reversed in order or in the same step as my time enable is set to on. I chose to give them all unique steps just to make it simpler. So once it starts to accumulate, the next thing that happens is, after the accumulate, is that the accumulate equals the preset. Once the accumulate equals the preset, it sets the done bit, which turns off the timer timing bit, and then it sits there just like that. The next thing that happens if something's going to happen, is you turn off input 0. So input 0 is set to 0. That's the bottom of the first column. That would be 9 if you're doing unique steps for each. Then if input 0 is set to 0, the run goes false. So the run goes false before the enable bit is set to off. I have the run 0 goes false, then the enable bit is set to off, then the done bit is set to off, and then the accumulate clears to 0. If you were going to use the same numbers that I did, in the first column it would be 7, 5, 2, 4, 6, 8, 9. And then in the second column, 10, 11, 12, 13. 3, and then the last one, 1. So I had you save your project as beginner L, your processor number, TON plus input.